Okay, so this project actually came out of a number of years of UHPC-related research at New Mexico State University. We started off looking at the development of pre-stressed girder and progressed all the way to the point where we built the bridge in the picture there. The right span is ultra-high-performance concrete produced with local materials, and the left span is high-performance concrete. It's a small bridge in southern New Mexico. So when Tran-SET was funded, we put in we got some input from New Mexico DOT. They were interested in using the ultra-high-performance concrete with local materials for bridge deck overlays, so we started in on this project. I'll talk a little bit about background, but going to kind of blow through that pretty quickly. Lots of experimental work in this project, so I'll hit that in pretty decent detail, go over some results that we've got so far on the project, and then wrap it up with some conclusions. The whole objective here was to just assess the ability of using ultra-high-performance concrete produced with local materials as a bridge deck overlay material. And anytime we talk about overlays, we need to realize that bond is paramount. Anytime we use mixtures that contain silica fume, the general philosophy is that we don't need bonding agents, so we've been fortunate there. And then there's been some work investigating ultra-high-performance concrete proprietary mixtures specifically as overlay materials. Devin Harris and Tess Alborn have a decent body of work there. And for the most part, they've stuck with textures between about 0.04 and 0.08 inches, which, I guess to put it in perspective, when we actually look at a bridge deck with surface prepped, we would like to see about 1/4 of an inch of texture, so as a minimum. So they've been able to get strengths with much less texture to their substrate, and we kind of focused on being able to match up with their work as opposed to looking at the minimum. We want to make the problem a little harder than what we actually have to solve. Ben Graybill has provided a cost comparison of different overlay technologies. The one on the left there is local UHPC, and it's quite a bit less than what he shows as the cost for proprietary mixtures, but that local UHPC bar just represents material cost, not construction cost, which is wrapped up into that one. So this bar really should be, just a little shorter than the proprietary mix bar. But, you're coming in pretty comparable to other technologies cost-wise. The mixture that we use is local materials. The things that we look for, we wanted to make the mix thixotropic. Workability for us, ended up with a grad student who didn't realize that slump is measured to the nearest 1/4 of an inch, so we threw in an oddball number there, but let's call it 7 to 7 1/4 inches. Spread of 10 inches. The thing that we do differently with our local materials is we replace an awful lot of silica fume in a traditional UHPC mixture with fly ash. Cuts the cost substantially. We also get by with a lot less steel fibers. The ductile overlays that they've been looking at have been about 3% steel fibers. We're trying to get by with about 1.5%, and it's all about cost, trying to reap, say, more than 50% of the benefits with less than 50% of the cost. The testing that we've done has focused on slant shear, split tension testing. Eventually we got to the point where we didn't like those tests, so we ran some direct tension tests. Looking at a range of textures, some of them were very light textures, basically no texture at all. We then looked at groove textures, and the reality is that when you produce a bridge deck and you've got hydrodemolition, you get a nice grooved texture that's quite rough, but trying to produce that on a laboratory-sized specimen is difficult. So you tend to try to come up with ways that you can produce a representative texture, and it's grinding or something along those lines, and it's not necessarily perfect. But we looked at some grooved textures that were produced by grinding in that 0.04 to 0.08 inch depth range, And then we had a rough texture, which was actually very little preparation. It basically just not finished, so we didn't get the coarse aggregate pressed down into the concrete and just hit it with a wire brush to knock off some of the slough. Wet cured it for 6 days, overlaid it, tested it 7 days after the overlay was applied. And the first test that we ran was the slant shear tests. In this case, you produce this cylinder with a 60-degree incline on the overlay surface or the bonded surface. When you load it as a cylinder in compression, you induce a normal stress, you induce a shear stress, and it's the shear stress there that we care about. That's the one that's actually giving us some indication of the shear strength of the bond. And then we ran split tension tests. We tried it with a split cylinder. Not to try to cast half of the cylinder horizontal, so we got away from that pretty rapidly. Allborn and Harris had done some work with split Prizm testing. The rest of the world actually runs split Prizm testing because they don't use cylinders. So we produced those specimens, got comparable strengths both ways, so I'm not so sure that there's a benefit either way. But for certain reasons, we decided we didn't like those tests either. We'll get to that when we get to the results section. So we ended up also looking at direct tension tests where we produced prismatic specimens with the substrate at the bottom, UHPC overlay, and then we cut essentially 2-inch cores, actually 1 7/8" cores, and tested those in direct tension. And the direct tension test was just like a pull-off test. It's got the pivot point both above and below when we do it in the lab to make sure that we get concentric loading on the specimen. Looked at shrinkage testing, both early age and long-term shrinkage. Basically, as your overlay material shrinks, it's going to induce shear stress on your bond. So we wanted to be able to quantify that. So the early age test was the LVDTs measuring displacements of hangers that were embedded in the concrete. It's a test that was developed by Erica Holt back in the late 90s. And then the long-term testing is actually the easy part. You've got solid specimens to monitor. Also looked at RCPT to make sure that we had reasonable impermeability against chloride penetration. Looked at coefficient of thermal expansion because you do want thermal compatibility between your substrate and your overlay material as well. Any differences there will also induce shear stresses on the bond. And now we've got some slab specimens that we've produced. No real results for these yet of combined shrinkage and thermal effects on slab specimens, and we're also getting ready to finish up the project with pretty close to full-scale testing of a channel girder that's got a UHPC overlay on it. For the slant shear specimens, we were looking for somewhere between, say, 1,000 and 1,800 PSI of shear strength on the bond. And even with essentially no texture at all, we were able to hit that minimum at 7 days. As we looked at different textures that were ground into the substrate, we continued to be within a reasonable range, and with the really rough texture, which is actually like 1/3 of what we would actually, well, a little less than half of what we would expect for minimum texture on a substrate, we were well above the range that we would expect to have or need to have. When we went to split cylinders and split Prizm testing, this time we were looking for about 150 PSI of tensile strength as a minimum, 250 as a maximum, 7 days. I don't think anybody complains about being too strong, and we had lots of them that were in excess of the 250 maximum. It really wasn't a problem to hit strength. The question was, are these tests good measures of tensile strength? I don't like indirect tension, I guess. I don't like the split Prizm test because mathematically it's supposed to be the same as a split cylinder test, but it's not clear to me that that's as good as it should be. So we ran direct tension tests, and now it suddenly became hard to get our minimum strengths. Still looking for 150 psi minimum strength at 7 days. With the rough texture, we actually started off with the grooved specimens. Didn't get strength, quite frankly, didn't even come close, and started to worry about it. Went to the rough texture to just generate more surface area. Didn't quite get strength again. And then it became a question of, is the surface actually adequate? When we grind the surface, my philosophy now is that that grinding process actually plugs up pore space and you don't get the bond that you really should. So we chipped specimens to that minimum 0.04 inch texture, and at that point we were able to get the tensile strength that we thought we should be getting. Shrinkage results, again, the whole intention of looking at shrinkage is because it induces shear stress on the bond. The early age testing on the left, really the number that we're interested in is what happens in the first 24 hours, and it looks like it's about 1,400 microstrain here. And at that point, we start on the long-term shrinkage plot where we pick up over the course of 28 days maybe another 450 microstrain, which makes it look like we've got about 1,850 microstrain of shrinkage, but the question becomes how much of that actually matters. And that's kind of where the last part of the project has to focus. During that first 24 hours, part of that shrinkage is happening in the plastic state, and it's not actually going to cause much of a problem for you on the interface. RCPT tests, well, UHPC is really dense, impermeable stuff, and we basically get negligible charges, ridiculously low. Nothing's happening in terms of getting chlorides into it. Coefficient of thermal expansion, though, it doesn't have any coarse aggregate in it, so it's going to expand and contract more than traditional concrete. So our coefficient of thermal expansion is about 70% higher than traditional substrate concrete would be expected to have. And then the last part of the project is looking at a series of slabs out here, all with overlays, different thicknesses, different mixes, and then the channel girder, which you can just barely see the end of it there, with a 1 inch overlay on it that we'll be testing in the lab this month, actually. And then to wrap it up, the bond strengths, you know, they're largely dependent upon texture. Texture is kind of a crucial thing. We don't really need a bonding agent as long as we've got decent texture, and by decent in this project we're actually talking about a lot less texture than we actually expect to have in the field. We got adequate bond strength from the slant shear tests, even when the substrate was insufficiently textured. We're well below what actually is required in the field. Same thing with split cylinder tests, great bond strength even with insufficient texture. Same thing with the split Prizm tests, great bond strengths, insufficient texture. They're just not, in my opinion, great tests to use to quantify that bond. The direct tension test is actually the one that I like, and that one was the one that was actually hard to meet. And we actually had to come up with a texture, well, a surface that was prepped in a manner that actually opened up the pore space of the substrate. And then when we look at the project in general at this point, right now it appears that UHPC is going to work out all right as long as we've got a bridge deck that's adequately surface prepped. And that's what I've got for you today, I guess. We've got some acknowledgments. I'll just leave them up there.